Pues gracias a vosotros por la invitación. Y bueno, como bien dices, aunque sea de esta manera, es igualmente una alegría conectar con unos amigos y compañeros. Y también les quiero felicitar a los organizadores porque yo estos días he estado conectando esporádicamente alguna charla, más que nada porque quería asegurarme de la diferencia horaria y de estar cuando tocaba en el lugar adecuado, que es delante de mi ordenador. Y la verdad es que ha funcionado todo estupendamente bien, así que mis enhorabuena porque ahora todo el mundo empezamos a tener experiencias de ese tipo y sé que no siempre es sencillo. Paso a mi presentación. La he preparado en inglés, entonces supongo que no les importará si ahora cambio de idiomas y luego si hubiera alguna pregunta quieren que la discutamos en castellano, evidentemente me va igualmente bien, pero como de esas cosas suelo hablar en inglés, eh, supongo que si la hiciera en español me encontré como en la transparencia a 12 con algo que no sé cómo se dice. Además, como pueden oír, yo siendo extranjero aprendí español en España y entonces hablo con esta inflexión muy para vosotros, para ustedes, muy curiosa.
No, está bien, como tú sientas mejor, adelante, Ricardo. Muchas
Okay,
gracias.
gracias. So I will now switch to English. Yeah, I will start with my presentation. As it has been said, recently my research activity has been focused on the study of phonon transport in insulator and semiconductors. Today I would like to share with you some of the results that we obtained recently with the class of interesting materials. This is the typical slide I use to introduce my talk and to motivate a little bit the interest in thermal transport. And here you can see like three big motivations to study thermal transport. One is thermoelectric devices and the need to be able to design materials that have a small thermal conductivity and a high electrical conductivity, because these materials are able to convert a temperature difference into electricity. And the larger is the electrical conductivity and the lower is the thermal conductivity, and the larger is the efficiency of these materials. So it's very important to be able to design materials with a given thermal conductivity, in this case a very low thermal conductivity. Then we have thermal management, which is, in my opinion, a topic which has been often overlooked, but it's really very important in the design of a nanoelectronic component and in the next generation emerging electronic devices. So normally when you buy a new computer or you read the tech data of some new computational node, you used to take a look at the clock frequency, which kind of give you an idea of how fast your processor is going to perform. So the thing is that nowadays, most of the microprocessor manufacturers would be able to design and fabricate processors with a higher clock frequency. But the reason they do not do that is that they would not be able to evacuate efficiently the heat that the processor produce, and so that wouldn't be a commercial object, because the product, the computer would simply melt down. So it is very important to be able to design strategies to evacuate as efficiently as possible heat. And then I have this last box, which is what I call phononics. Phononics, maybe it's a word that you can use in a more general sense, but I prefer to keep it for that subtopic where you use phonons to encode logical information and to process information. In our group, we try to tackle these three big challenges in different research lines. We have studied a lot of lattice defects and how they scatter phonon transport. Also, we have been quite active in crystal phase engineering, which is a subfield in nanowire science, which is becoming increasingly important. And the thing is that when you grow a nanowire, you're able to stabilize crystal polytypes, which are different than the one that you have in the bulk. And so, for instance, you can have wurtzite gallium arsenide or wurtzite gallium phosphide, or you can even have hexagonal silicon. Of course, these different crystal polymorphs have different properties, electrical and also thermal properties. And what it's really intriguing is that our experimental colleagues are so smart that they are able to grow heterostructures where, rather than combining different materials, like in this cartoon, you have, you have systems where the material is the same, but what you change is the crystal phase. And so you can have like a kind of super lattice where you are only modulating the crystal phase. Then we have some activity in 2D materials, because sometimes it seems that in condensed matter, if you don't do anything with 2D materials, you're not on the map and you're not recognized. And then we have also been working on thermal rectification, so on the simplest possible phononic devices, so a device that rectifies heat flow, or more modestly, where the thermal conductivity depends on the direction of propagation of the heat flux. In today's talk, I will focus on this last big motivation, which is phononics, and so the use of phonons to transmit and encode information. What do I mean with that? Well, information technology is, in a nutshell, is very simple, and it's based on the transmission of energy and on our ability to modulate it. So if you look at the man here on the left-hand side of this cartoon, if you set a fire and you are far away, you can see that there is a fire or there is not a fire. So it's a rather crude information. But if, like this guy, you use a blanket to modulate the smoke that come out of your fire, you can start transmitting a slightly more sophisticated information. So if you bring this approach to the extreme, you end up with the CMOS transistor, which is our standard nowadays for a sophisticated way of treating information. Okay, so if you need energy, you want to modulate it. Well, nature offers you different kind of energy, not only charge carriers. Charge carriers, of course, are very important. They are the backbone of the current solid-state electronic technology, but you have different opportunities. You have electromagnetic radiation, which we already use, like, for my mobile phone here. You have photons for optical communications, and then you are left with heat that I guess it will not be difficult for you all to recall your thermodynamics class and remember that heat is always regarded as a source of loss. Okay, so the challenge in phononics is try to reverse this viewpoint and try to look at heat as an active source of energy that you can use to transmit in a deterministic and ordered way your information, and if possible to modulate it. There are very good reasons why this hasn't been done so far, and why my mobile telephone or the processor that are making my laptop work right now do not work with phonons. And is that phonons are very peculiar quasi-particles. They have no mass and they have no net charge. So it is very difficult to tell a phonon what to do. Because when you are propagating an electron or an electromagnetic wave, you can always use an external field to like accelerate it or slow it down or deviate it, but you cannot do that with a phonon. However, what I would like to do in today's talk is to challenge this statement and show you that indeed you can use, for instance, an electric field to do that. Of course, it is true that the phonon as a quasi-particle has no mass and no net charge. So if you think in a very simplistic way of a phonon like a quasi-particle traveling in space, it is true that you cannot use an electric field to slow it down or to accelerate it. But phonons are collective vibration of the lattice. So if your lattice is polar, you can affect the lattice, and then in turn it would affect the propagation of the phonons. So in this simple analogy, if the phonon is this small particle traveling on your desk, you are not able to slow it down with the electric field, but you can use the electric field to, for instance, to roughen a little bit your desk and to make the motion of the phonon through through the propagation plane more difficult or easier. Okay. So what is that we do? As I already hinted, we are a theory group, so we do numerical simulations and we try to provide insights from atomistic calculations of heat conduction in nanostructural systems. And what I will discuss today is some of our recent results with the prototypical ferroelectric oxide, lead titanate. And I will show that phonon transport can indeed be dynamically manipulated with electric fields. And this, in the end, could lead to the design of phonon devices, such as phonon transistors, phonon switches, and phonon polarizers. The good thing for the audience, I believe, if you are not expert in ferroelectrics, is that I'm not an expert either. So I guess I know just the right amount of thing that you need to follow the rest of the talk. And so this is what I will try to explain in this introductory slide. So if you know nothing about ferroelectricity, you're about to learn everything I know in just one slide. So this is a prototypical case of a perovskite ferroelectrics. This is a lead titanate, the material that we will be discussing throughout the rest of the talk. So you see that it has a unit cell which is almost a cube. You have lead atoms at the corners, oxygen atoms at the center of the faces, and then you have here in the middle the titanium. And if you look closely, you will see that titanium is not exactly at the center of the cell, and it has a displacement upward in this case. Okay, so this is because below a certain temperature, a certain critical temperature that in the case of lead titanate is very high, is more than 700 Kelvin. The crystal favors a ferroelectric distortion, so it lowers its energy by displacing a little bit the titanium atom, which is not in the middle of the cell, but it's slightly displaced. If you go above this critical temperature, then on average you have a situation where the titanium atom is exactly at the center, and so you have this different crystal symmetry. And what is important is that as titanium and lead and oxygen has different nominal charge associated, because all these bonds are polar, when you have this distortion, your system is ferroelectric in the sense that it has a permanent dipole moment associated, while here this is no longer true and the system is paraelectric. Okay, but this is a technical detail that you would be interested only if you are really into theory, and just a slide about the kind of code that we use. It's a kind of effective Hamiltonian code, which is parameterized against first principle density functional theory results. And we will use this to perform different kind of simulations. So I will both discuss molecular dynamics results or calculation of the thermal conductivity based on the solution of the phonon-Boltzmann transport equation. But again, my goal here is not to enter into the detail of the computational methods. So every slide has a small indication what is the computational method considered in that case. But then, I mean, if anybody is interested, I'm always available to answer questions. So I would like to start with what historically has been the first topic that we tackled. And I think also it's very useful to introduce the whole idea behind this electric field manipulation of the lattice. So now you already are as expert as I am of ferroelectric perovskite. So this is the ferroelectric ground state. So in this case, we have arbitrarily chosen to have a ferroelectric distortion like upward. Okay, so this is interesting because as this ferroelectric distortion has an associated dipole moment, the thing is that you can use an electric field to manipulate this permanent electric dipole moment. And for instance, you can reverse the polarization. So if you look at this lattice and this, they're exactly the same. So they are two equivalent ground state, but you have reversed the polarization from up to down. Okay, so here is the first idea we came upon. So you can imagine to have a material which is in a monodomain state. So you have your ferroelectric ground state and all the dipole moments are pointing upward. Okay, but then you use your electric field and you switch the polarization in half of the material. And this is something that our experimental colleagues can do with a reasonable degree of control. And so you end up with the system where you have half of the system with the polarization up and the other half with the polarization down. Okay, so here the very simple idea is that this is the uniform case, and so you expect to have a kind of high thermal conductance because all the phonons are eigenstates of the system, though they can travel unperturbed. Well, as a matter of fact, they have anharmonic coupling, but we'll come to that later. But then if you have this kind of boundary, we don't know yet how much, but it will scatter to a certain extent phonons. So what is interesting here is that as you can reverse the polarization in one of the two halves of the material, in a way you are writing and erasing the boundary. Okay, so you have a boundary which is going to be a scatter source, and you are able to write and erase it at will. Okay, so the simple idea is this one: you have a high conductivity state, and you can use an external voltage to commute to a low conductivity state. And then once you come up with this idea, of course, it's very easy also to speculate that you could write more domain walls and to encode an even lower conductivity state. Okay, so to test this intuitive idea, well, we are atomistic theoreticians, so we set up our theoretical atomistic model, which you see in this picture, and we let the phonon flow through the system. Okay, so in this case, we use a technique which is called non-equilibrium molecular dynamics. It means that it's something pretty close to an experiment. You have your chunk of material, you connect one end of the material with a hot thermostat, you connect the other end to a cold thermostat, and then phonons will start flowing from the hot end to the cold end. Okay, so in this graph, please only look at this half because it's mirrored because of technical reason of the calculation. So you can focus on this part. You see that this is the temperature as a function of the position, and the temperature is dropping from the hot to the cold value. Okay, so if you look here in the middle, you can kind of see a linear region, and then by making use of a Fourier law, you can calculate the thermal conductivity of your system. In the plot below, you see the polarization as a function of the position, but here there is no surprise because the system is a monodomain, so all the polarization are up. So throughout all the system, you see that the polarization is almost 0.5 in the direction, in this direction of the distortion. In the direction entering the screen, it's 0. Okay, good. So now we can write our domain wall. So this is easy to see now in the lower plot. You see here we have the distortion up, and here we have the distortion down. So the polarization goes from plus 0.5 to minus 0.5. And you see the transition is rather abrupt. Okay, the polarization entering the field, entering the screen is always 0, and it has a small glitch as predicted by the theory at the domain wall, so at this boundary that we have written. So if you look again to the plot of the temperature as a function of space, of the spatial coordinate, you see that it's similar to before, but here, if you look close, and here you have a zoom, you see that it has a jump, and this jump is the signature, is the smoking gun that you have an interface thermal resistance. So you evaluate this temperature jump, you divide by the heat flux, and you have your thermal boundary resistance. So in this first simple calculation, we were able to show that we can increase the overall thermal resistance by approximately 20% for the system size, which is a kind of realistic size also for an experiment. So, okay, well, we are happy, but of course now we want to do more. Now we want to be able to increase it more, the thermal resistance, because 20% is okay, but we would like to be able to do better. And so, well, it's simple. In principle, you just write a second domain wall. Here we are a little bit limited by the computational cell we can afford. And of course, it's very difficult to fit two domain walls in the same cell, but we kind of did it here. So you see that polarization goes from 0.5 to minus 0.5 and then again to 0.5. So here we have two domain walls, okay? And so here, again, you have two small jump in the temperature profile, okay? What resistance associated to domain wall do you expect? Well, if the domain walls were infinitely separate, the resistance would be twice as much the resistance of one single domain wall. But if they are rather close, when phonons come, they will see like a cluster defect. And so the total resistance is not twice the one of the one single domain wall, but it's kind of 1.4, 1.5. Okay, so here you have a little bit of trade-off when you design your system, because if the domain walls are very separate, indeed you have an interface resistance which increases linearly with the number of domain walls, which is what you want. But if they are very separate, you have a lot of material between the two domain walls, so the relative weight of the thermal boundary resistance on the overall thermal resistance is going to be slower, and so your thermal switch is not going to be very effective. And so you have to play a little bit with these two variables. Okay, we decided to tackle the same system also with a different computational technique, which again you don't need to know anything about for the purpose of this talk. Non-equilibrium grain functions. What is important is to know the complementarity that they have with the non-equilibrium molecular dynamics. So in the calculation I discussed so far, you have a full anharmonic order included, so you have all the phonon-phonon scattering processes correctly described. The simulation tends to be more reliable at high temperature because it's where you are allowed to consider the motion of the ions classic. And unfortunately, you have a size effect, so you are supposed to use increasingly large supercell to make sure that you are converged in your size. But when you go to equilibrium grain functions, it's different, because here the only scattering you have is at the harmonic level. So there is no phonon-phonon scattering, so the only scattering source is the elastic scattering at domain wall. It's a bit idealized, but it's very practical to analyze exactly what happens at the domain wall. They are reliable at low temperature because it's where you expect an harmonic effect not to be very important. And in principle, you have no size effect. Okay, so let's just take a look to the results we obtained with grain functions. And it's nice because, well, the quantitative estimate is very, agree very well with the value we extracted from molecular dynamics, but you have some extra insight. On the one hand, this is the typical result from this kind of simulation. You have a transmission spectrum, and here we can see that the scattering that we already described with molecular dynamics essentially comes with high frequency phonon, and here low frequency phonon does not really see this boundary, and then they go through it almost unperturbed. And then what is perhaps more interesting is this other graph here, where you see a little bit again in a different way what I was discussing before. So you have one domain wall, so you have a decrease of the thermal conductance. You add a second, and there is practically there is no change, because here you have a first domain wall, so phonons go through, and some of them are killed and are reflected by the domain wall. So when you have a second domain wall, you cannot kill twice the same phonon. It's already dead. It's already reflected after the first interface. And here, as you don't have anharmonic coupling between phonons, you cannot rebuild the equilibrium phonon population between the two scatterers, what happens in molecular dynamics. And so when you are doing your filtering effect with the first domain wall, and when you hit the second domain wall, almost nothing happens. Okay, so this is by construction of this computational technique, which is fully harmonic. In molecular dynamics, this happens only when they are close, because they don't have enough time to randomize again and to recreate the equilibrium population. But you do observe that when they are very, very separated. Okay, so you have these complementary views on the same physics. And finally, about this topic related with domain walls, we looked even closer, and we could see that these domain walls are not democratic scatterers. They like to scatter especially some kind of phonons. So phonons like this one that vibrate like perpendicular to the interface, they go through the interface almost unperturbed, while phonons where the vibration is parallel to the interface, which is exactly where you create the defect, your boundary, these are the ones that are scattered. So not only you are scattering phonons, but in a way you're also selecting a given polarization. And so these boundaries can also work as phonon polarizer, which is rather remarkable. And well, as often happens, you are very happy with the results, and you discover that there was a way easier, an easier way to have a phonon switch, much easier. This is the thermal conductivity as a function of temperature of lead titanate, of the ground state. Okay, lead titanate, if you remember this, the lattice is anisotropic, and so we expect to have two independent components. One, which is parallel to the polarization, and two degenerate components that are perpendicular to the polarization. Okay, so the one parallel to the polarization is the blue curve, and the other is the red curve. Okay, so now you do your experiment. For instance, you have this is your chunk of material, and you make phonons flow in this direction of the arrow. Okay, so phonons flow perpendicular to the polarization. So what the thermal conductivity you are seeing is the high conductivity state, this one. Okay, so if you were able to rotate your sample, then you would have an efficient phonon switch, because when you rotate it, if you don't change your transport setup, you're still making phonon going from left to right in the screen, and so you would be seeing the blue electrical thermal conductivity. Okay, of course it's obvious that it's not very practical to rotate the sample, but with the ferroelectric you don't need to rotate the sample, because you can rotate the electric field, the polarization with an electric field. Before we used an electric field to reverse the polarization, but you can also use an electric field which is perpendicular to polarization, and you can rotate it. Okay, so if you fully rotate the polarization, you have now exactly the situation. It's like if we have rotated the sample. So it's much simpler than what I discussed before, because here you just play with the monodomain. You don't have to write domain walls to control the separation, the number of domain walls, and the change is sizable, because if you look at 300 Kelvin, it goes from like 15 maybe to 30. So it's a very large gain with a simple strategy like this. You use an electric field and you rotate the polarization. Okay, now next, what I would like to discuss is a slightly different case, but also in the same line. So now I want again to apply an electric field, but I don't want to reach the coercive field. The coercive field is the minimum electric field that you need to reorient, fully reorient in a stable way the polarization. So if your polarization is like this, you start applying electric field opposite to it, and when you reach the coercive field, this polarization will flip. And the same if you go perpendicular. You start pushing, you push it, you push it, at some point, it will again commute and fully rotate. Okay, so now I want to apply an electric field, but I want to stay below the coercive field. Okay, in this case, what I can do is scan an all range of electric field value, while in the setup I discussed before, it was only up, down, up, down, up, down. Okay, so I want to study a little bit with more detail the correlation between electric field and polarization. So in this case, I am stretching more and more the polarization, and in this case, I am damping, I'm compressing it. And in the second case, I will be careful not to damp it too much, because otherwise I would make it commute, which is something that what I did before and what I don't want to do it now. Okay. Okay, so now you're already familiar with the good old thermal conductivity as a function of temperature of lead titanate. It is anisotropic. And now I will start applying electric field, in the direction parallel to the polarization. And as you see, at all temperature, it is consistently increasing. Then I push a little bit more the electric field, and I push a little bit more. So it increases in a very almost linear way. And in this inset, you have the relative variation. Okay. Now, what is cool is if I do the opposite, now I go against the polarization, I decrease it, and I decrease it. So I really have a full modulation of thermal conductivity with an electric field, remaining below the coercive field. Okay. So, well, we are theoreticians, so when we do this, we have all the equations encoded in our programs, and so this is very nice because you can really track down the variation. It's also challenging because if you don't know why any parameter we are measuring varies, it's just because you are not smart enough. It's not like when you do an experiment that you are unknown events or no factors. Here everything is under control, and so we took a look and we saw that here the situation is very simple. So when you apply an electric field which is parallel to polarization, you are just hardening all the phonon modes, which this in turn will give a change in the lifetimes. And when you go against the polarization, so you damp it, you are softening all the phonon modes. And so this is what happens in your material. What is interesting is what you do now if you apply an electric field which is perpendicular to the polarization, because the physics is completely different. So again, I will apply electric field in this way, but not enough to make the polarization fully commute and go like this, as I did before. I want to, I want just to scan all this potential landscape, okay? And I want to evaluate the electrophotonic coupling between the gain between applied electric field and change in thermal conductivity. So in this case, I've broken the degeneracy, any kind of degeneracy. So I have 3 independent thermal conductivity, and here I'm already I go directly to the relative change. And you see that here the change is even larger than before, because look at here. Here we have decreased the thermal conductivity of more than 50%, which is amazing. And here again, well, we did our homework and go look into what was happening. Here it's interesting because the physics is a bit different. Here the thing is that when you rotate the polarization, you will see clearly here, when you rotate the polarization, you decrease the symmetry of the lattice. So you break a lot of degeneracies in your phonon spectrum, and you are just enabling more phonon-phonon processes that before were forbidden by symmetry. And as you have more possible phonon-phonon scattering events, you have a thermal conductivity which is lower, as you can see in all the direction that you consider. Okay. Well, this is a small parenthesis. Of course, we were very excited by these results, so we also tried to do it with the strontium titanate. We expected a larger electrophotonic response because of the larger electrical susceptibility, but that was not the case. So we are not very happy about that. But we are lucky enough because just like when we were working on this topic, an experimental paper came up, and we have a remarkable agreement with the experimental results, so we could provide some additional insight in those experiments. Okay, so now I'm moving toward the end of my talk, and I would like now to discuss a way to increase the gain of my electrophotonic response. So if you think a little bit, in the first set of results, I was applying pulses, discrete pulses of electric field to stimulate commutation events of the polarization. I wanted to reverse the polarization from here to here or from here to here, but I just needed pulses, okay? Strong pulses, because you need a strong electric field to make this happen. The coercive field are high. Well, let me open a small parenthesis. The electric fields are high, so if you look at the number, you might in principle be a little bit afraid, because this could not be done experimentally and so on. But this is not the case, because all these experiments, they are done on very thin films. So even if the electric field that you need is large, if you work with a thin film, normally with potential differences of the order of fraction of an electron volt, you can make it happen. So this is completely feasible. Okay. In the second part of the talk, I could do things with lower electric field because I didn't need to reach the coercive field, but I needed the electric field to always be on. Okay. Now, I like this second approach. I will continue on that, but I would like the response to be larger. Okay, so I would like to have a similar change in thermal conductivity, but triggered by a smaller difference in the applied electric field. And this can be done indeed. Okay, so what I discussed before is exactly the following. I have a polarization in one direction. I use an electric field to rotate it and to come up with a different direction. Okay, fine, this works and we can do it. It turns out that you can do this in a left-handed thin film also with strain. Okay, so for instance, you can deposit your thin film on a mismatched substrate, and if you stretch sufficiently the thin film, it comes a time where it favors to have rather than having a polarization out of the plane or of your substrate, in plane of the substrate. Okay, so here I'm not proposing to use strain instead of electric field. Of course, you can also do that, but strain, it's, I mean, you need a mechanical deformation, so it's not really the first thing you think of if you want to design something that you would call a device. Here I'm going in a slightly different way. So I can use strain just to create my, my starting point. So if I strain the lattice, where I grow if I strain the lead-titanium lattice, because I grow it on a mismatched substrate, if the strain is sufficient, the polarization will be in plane. Now imagine that I strain it sufficiently so that it's really on the verge of the rotation, but it hasn't rotated yet, okay? Just, I mean, if just strain a little bit more and it will rotate, okay? If I am there, practically you can rotate the polarization in an effortless way, because it's really just because of the strain, just about to rotate. So you only need a very tiny electric field to make it happen, okay? And you see this in these plots. So this is the polarization. This is nothing thermal yet. So you look at the black curves. So here the polarization is all in the Z direction, which is like 0.8 something, and here it's 0. But then you increase the strain and it switches. You see, now it's fully polarizing the other way. You have rotated the polarization. In red, you see the susceptibility, which is the derivative of the polarization. And then when you have this transition, you have a virtual divergent susceptibility, or at least a very large susceptibility. Okay. And the same happened with thermal conductivity, of course. Here, it's, I think this is all for room temperature. This is the case we discussed before. You have this and this thermal conductivity. Okay. But then you start to strain. And then it comes a time where rotating the polarization happens almost for free. And so this alpha, which is in our formulas, it's like the electrophonic coefficient, the gain in the response, have this very large jump. Okay, and so, well, here we are not really sure if you can make this jump higher and higher depending on how fine you look in your simulation. But of course, each one of these points is a set of a complex simulation, so we didn't push it further. Okay, so in a way, it's like you know, in the first, you know, that referee that always reject your papers and you hate it. Okay, so you want to do him something really bad, and so in the first scenario, you go picking up at a train station, you took him for a long walk, and then when suddenly you see a cliff, you push it down the cliff. Okay, and then from now on, all your papers will be accepted. Okay, it works. Of course, I'm not suggesting that you do that, but it's just a funny metaphor. But you have to do some work. You have to, you know, all the way to the station. This other situation, you're already on the cliff. So you're there because of the strain, and you only need a little push, and your friend, you fall down, and your polarization will switch, and then you have this very large response. So I guess that I'm heading towards the conclusion. I think that my main message here is that yes, indeed, perhaps the main take-home message is that you can manipulate polar modes, and you can use this manipulation to have a coupling between a lattice and phonons, electric field and phonons, and you can use this for the dynamical control of the heat flux. Okay, I show you that domain walls can be written and erased with an electric field, and the thermal resistance can be switched on and off, and then you can use that mechanism to have your your thermal switch. And also I showed that these domain walls, they behave as polarizers. In the middle, just in one single slide, I showed that there is a much easier way to design a thermal switch, and it just taking advantage of the anisotropy of the material and the possibility to rotate the polarization. And finally, I moved my attention to a continuous modulation of thermal conductivity. So not this up and down. If you want, in the first part, I was dealing with a switch, so a digital transistor with on-off or 1-0. And in this case, I'm going analog, and so I modulated thermal conductivity throughout all the possible range before I reach the coercive field. And you can do that again with the electric field, and you can use strain to enable a giant electrophonetic response, so to increase, in principle, as much as you want, the gain in your device. This is the funding thanks to which we're able to do this work. And here I have a bunch of references in case you wanted to know more. But if you are lazy or don't want to go through the papers, you can always send me an email, and I would be happy to discuss with you. Thanks for your attention.
Hola, Ricardo.
Sí, aquí estoy.
Gracias.
Vosotros.
Es que empecé a tener mala recepción. Muchas gracias por tu charla. Entonces, vamos a pasar a la sesión de preguntas. ¿Pueden irlas haciendo directamente, por favor? Miguel Mayorga, adelante, por favor. A ver, aquí está una...
Hola.
A ver, aquí está una pregunta de Miguel Mayorga.
Hola. ¿Se me escuchan?
Sí, sí, se escucha. Adelante.
Hola, Miguel.
Hola. ¿Han considerado efectos cruzados entre los gradientes? Por ejemplo, el gradiente de temperatura.
Entonces, sí y no, digamos. Cuando empezamos no es algo que miramos, pero sobre todo digamos, en la segunda parte de la charla, los resultados que he discutido ahí los obtuvimos resolviendo la ecuación de Boltzmann, y ahí tienes ya de regalo todo el tensor de conductividad térmica. Y entonces efectivamente hay términos cruzados. Sobre todo cuando aplicas campos perpendiculares puedes tener términos cruzados, entonces digamos que puedes aplicar gradiente en esa dirección y tener algo de transporte térmico perpendicularmente. Sí, eso puede pasar.
Muy bien, gracias. Thanks for your talk, by the way.
¿Alguna otra pregunta, por favor, del público?
Yo tengo una pregunta.
Adelante,
Hola, Alejandro. Adelante.
¿Qué tal? Gracias por la plática, estuvo muy interesante. Tengo una duda. ¿Han visto si es posible igual modular estos efectos en perovskitas híbridas con moléculas como la de metilamonio?
No, me parecería muy interesante hacerlo. El problema, digamos, ahí, bueno, son problemas mundanos del cálculo, ¿no? Si quieres hacerlo con dinámica molecular, necesitas un potencial clásico interatómico bien parametrizado que te permita simular esos sistemas, de los cuales yo no soy experto, pero si existiera, en principio lo puedes hacer. Hacerlo con ecuación de Boltzmann, ahí en principio no tienes problemas porque puedes calcular las constantes de fuerzas con DFT, digamos ab initio. Ahí el problema es que el coste computacional empieza a subir, ¿no? Porque esos materiales, como donde yo tengo un átomo, tú ahí tienes un pegote de moléculas, el número de átomos que vas a tener en la celda de unidad va a crecer mucho, y entonces sospecho que el cálculo sería rápidamente inviable. Pero en principio lo que dices tiene sentido y se podría mirar, y debería, siempre es atrevido, podría funcionar de la misma manera.
Sí, porque ahí lo que me podría causar algo de ruido es que la molécula también puede rotar dentro de su eje, entonces a lo mejor eso
Claro.
también podría cambiar su magnetización, ¿no?
Sí, sí, eso puede pasar, o es como en líquidos iónicos, ¿no? Donde tienes tiene conducción iónica y conducción electrónica mezclada y tienes diferentes niveles de desorden cuando subes en temperatura.
Muchas gracias y gracias de nuevo por la plática.
No, no, a ti. Y si progresas en esa línea o si la atacas, tendré curiosidad de conocer los resultados.
Pues más o menos ya tenemos constantes de fuerzas de algunas perovskitas híbridas que
Muy
hicimos con
bien,
DFPT, pero pues ahí vamos poco a poco.
muy bien, pues ya me contarás.
Claro.
Bueno, hay otra pregunta de Fernando. Adelante, Fernando.
Gracias. Buenas tardes, Ricardo. Una plática bastante interesante.
Gracias.
Yo tengo varias preguntas, pero la que más me está inquietando ahorita es que los compuestos que estás trabajando, veo que ahí aparece como elemento común el titanio.
Sí.
El titanio pues tiene bastantes electrones. En ese sentido, pues es susceptible a los efectos de campo eléctrico y de campo magnético. Entonces, mi pregunta es si estos resultados te permiten entender la interacción del titanio con los elementos alrededor y si el control de la resistividad que nos presentabas necesariamente requiere que se involucre un elemento como el titanio en los elementos.
Digamos, en principio yo diría que no, pero digamos, aquí la idea es que si tú tienes una red polar que pueda responder a un campo eléctrico de forma eficiente, digamos, tú lo que apuntas es que el titanio va a favorecer una respuesta fuerte con el campo eléctrico. En principio eso dependería de la susceptibilidad del material. Entonces, quizás, digamos, mi conocimiento de esos materiales es escaso para que te pueda dar una predicción general. Pero la verdad es que sí, lo que dices tiene razón, porque nosotros lo vemos con titanato de estroncio y con titanato de plomo. No lo sé. Es posible que tengas razón, pero no puedo decirte la ciencia cierta. Habría que mirarlo con algún otro ferroeléctrico que no contenga titanio. Supongo que ahí una indicación ya podría ser, porque eso tiene que estar tabulado en la literatura, ver en diferentes compuestos cuál es el campo coercitivo, ¿no? Porque eso te da una idea de cuánta caña tienes que meter al material para que switchar de un estado de polarización al otro. Y entonces eso a lo mejor da alguna indicación, alguna pista de cómo va a ser la respuesta de la red a un campo eléctrico aplicado. Luego, lo que sí, eso diría que no tiene mucho que ver con la identidad química de los elementos, dada una distorsión como que procesos fonón-fonón se activen o se dejen de activar y te cambien la conductividad térmica, eso sí que mi intuición no me ayuda y tendré que hacer el cálculo numérico para medirlo, eso no lo sé.
Ok, gracias, Ricardo.
No, a ti. Y entiendo que no he respuesto del todo a tu pregunta, pero me parece interesante lo que apuntas.
Bueno, muchas gracias, Fernando. Hay otra pregunta, creo que por ahí levantó la mano Álvaro. Álvaro, ¿sí?
Ya estoy aquí.
Hola, Álvaro.
Bueno,
Hola, Ricardo. Oye, muchas gracias igual por tu plática, muy interesante como siempre. Bueno, vi que estás trabajando estos materiales, con estos materiales con titanio. ¿Esto qué tan complicado sería implementarlo, por ejemplo, con capas? Por ejemplo, no sé, hay una capa que recientemente estamos por estudiar, que es una capa de oro y cobre. Entonces,
Sí.
por ejemplo, ¿qué tan complicado sería implementarlo o aplicarlo en este tipo de materiales, nanoestructuras?
Bueno, digamos, yo lo que entiendo es que, digamos, nuestra idea cuando hacemos un cálculo para proponer un experimento, para proponer un diseño de dispositivo, es que se haga con una capa delgada. Nuestro cálculo evidentemente no es de capa delgada porque sobre todo todos esos cálculos de ecuación de Boltzmann son cálculos donde necesitas que sea un sistema tridimensional periódico y si no la celda unidad te crece demasiado para que el cálculo sea viable. Entonces nosotros de momento estamos haciendo la aproximación de trabajar con el bulk y extrapolar ese comportamiento al caso de capas delgadas. Digamos, la idea es que la capa delgada va a tener propiedades de bulk, pero al mismo tiempo, por su naturaleza de capa delgada, permita implementar lo que nosotros proponemos. Por ejemplo, si tú coges el bulk, nunca vas a poder rotar una polarización, porque el campo eléctrico que te sale tabulado se corresponde a una diferencia potencial inmensa. En una capa delgada, eso de repente se hace viable porque con una fracción de electron-volt, con una fracción de voltio, perdón, le puedes dar la vuelta a la polarización. Pero los cálculos que hemos hecho aquí siempre, digamos, se hacen con materiales tridimensionales bulk.
Ok, perfecto. Bueno, pues muchísimas gracias, Ricardo, nuevamente.
Bueno,
Nosotros.
hay otra pregunta de Luis Gerardo Ribé. Dice, ¿la leo, Luis Gerardo, o preguntas? Pero bueno. Adelante,
Sí,
Luis Gerardo.
si la puede leer por mí no hay problema. Estoy muy emocionado porque no sé si estoy bien o mal, pero hay una relación del cambio del spin, ¿verdad? Con este estudio. Mi pregunta es, ¿hay alguna tabla que podamos utilizar para poder calcular en una superficie en metros cuadrados, por ejemplo, una energía aplicada, el cambio de temperatura o el cambio del spin, bueno, de polaridad? Esa es mi pregunta, una fórmula o alguna tabla que ustedes tengan más desarrollada. Muchas gracias y felicidades.
Espera, no te vayas, Luis. Espera, elabora un poco más, porque es que al principio no te he oído bien. Entonces, una tabla que relacione, perdón, el cambio.
¿Me escuchan?
Sí, ahora sí.
Ok. El cambio de polaridad por, digamos, por superficie, por metro cuadrado, y con la aplicación de la energía, por ejemplo, si se aplican, por decir una cantidad muy elevada,
Sí.
25 gigawatts en 1 kilómetro cuadrado, si hay una tabla que pudiera darme el cálculo del cambio termal o del spin de la polaridad de esa área.
Sí. Mira, ahora no puedo, digamos, necesito un poco de tiempo para contestarte porque yo, digamos, en estas colaboraciones soy el experto, entre comillas, de fonones y los expertos de ferroeléctricos son mis compañeros. Pero yo creo que sí, que, digamos, tu pregunta tiene respuesta. Lo que me temo es que aunque hay, una vez más, yo no soy el experto en esos materiales, pero creo que el metro cuadrado de capa delgada de nitado de plomo es algo que de momento está fuera del alcance de la tecnología actual. Más que nada, lo que pasa es que mucho de lo que proponemos nosotros se basa o en tener un monodominio, donde toda la polarización está bien orientada, o tener un multidominio, pero un multidominio diseñado, ¿no? Donde exactamente donde tú quieres tienes una frontera de dominio y las polarizaciones cambian. En la realidad, no, la realidad, como desgraciadamente a menudo ocurre, no es tan bonita y entonces típicamente cuando tú tienes una capa delgada que supera cierta superficie, se te forman espontáneamente multidominios por compensar la polarización y evitar, digamos, respuestas
Claro.
de polarización divergentes.
Sí, claro, claro. Y una pregunta, ¿la energía aplicada puede sobrepasar alguna superficie, digamos, ir y penetrar en donde uno quiera aplicar en
Sí,
una
yo diría,
sí.
digamos, ahí todo lo que nosotros necesitamos en nuestra propuesta teórica es un campo eléctrico. Entonces, si encima de la película del gas de tinato de plomo tú tienes 4 capas de un metal, yo qué sé, siempre y cuando tú seas capaz de aplicar un campo y ese campo lo pueda sentir en la película de tinato de plomo, no hay problemas ahí.
Ok, muchas gracias, muchas felicidades.
Sí, gracias.
Gracias.
¿Alguna otra charla? ¿Alguna otra pregunta, perdón? Charlas espero que nos des muchas.
Espero que la próxima sea presencial.
Sí, nosotros esperamos también que nos visites por aquí y que podamos compartir una taza de café cara a cara o una
Muy
cerveza
bien.
o un buen vino. Bueno, ¿alguna otra
Mejor aún.
pregunta? Tenemos un poco de tiempo, así es que pregunten. A ver, Fernando, creo que estás levantando la mano, Fernando, ¿o no?
Sí, es correcto.
Adelante.
Ricardo, me surge otra pregunta, y esto es un
Sí.
poco más del proceso físico de lo que nos platicabas. Cuando se pone el campo eléctrico en el sistema, que se mueve el titanio de posición, dirías que la modificación de la conductividad térmica que las gráficas que nos presentas se debe justamente a la modificación de los enlaces que tendría que ver directamente con las constantes eléctricas de la estructura.
Digamos,
Como que no me imagino bien el proceso físico que ocurre al interior de la estructura.
digamos, la constante dieléctrica es importante porque es la que te da, que te describe tu habilidad de modificar la red cuando aplicas un campo eléctrico. Pero si no, digamos, el campo eléctrico en ese caso es nuestra herramienta para modificar la red. Tú podrías pensar que la modificas con otra manera, porque, por ejemplo, mira, en la última parte de la charla, cuando he descrito el caso del strain, eso será lo mismo. Tú aplicas strain y con aplicar el strain modificas la red. Y entonces, digamos, yo creo que el caso más, que más bien se entiende y más bien se explica es cuando tú tienes tu sistema ferroeléctrico, la polarización, por ejemplo, arriba, y la vas rotando un poquito. Por ejemplo, imagínate la rotas 5 grados. Al rotarla, tú imagínate que calculas bandas de fonones de tu sistema. Entonces, cuando la rotas, como has roto un poco, has disminuido la simetría, vas rompiendo degeneraciones. Entonces, antes tenías una banda que eran 3 bandas degeneradas, me invento, ahora las has roto un poco. Entonces, tú a ese punto Q de tu espacio recíproco, ese punto Q de tu estructura de bandas, antes tenía solamente un posible proceso que conservaba energía y momento, y entonces podían intervenir 3 fonones para dar un evento de scattering, y ahora tienes 3. Y entonces simplemente al disminuir la simetría, eso de hecho es una tendencia generalizada, ¿no? En cuanto más grandes sean las celdas primitivas de materiales, que quiere decir simetrías reducidas, más procesos de fonoscattering puedes tener y conductividad térmicas más bajas tienes. Si tú coges, yo al principio mencioné brevemente que ahora trabajo en Crystal Phase Engineering, ¿no? Digamos en politipos no convencionales de semiconductores. Si tú coges el arsenuro de galio, que es una 5 blenda cúbica, que tiene 2 átomos en la celda primitiva, y pasas a la bursita, que es hexagonal 2H y tiene 4, solo por tener 4 tiene más bandas fonónicas, no hay secreto ahí, ¿no? Las bandas son número de átomos por 3 y entonces tienes 12 en lugar de tener 6. Y al tener 12, si tienes suerte, tienes exactamente los mismos procesos de scattering que tenías antes. Pero si no la tienes, solo puedes tener más, no puedes tener menos, porque al tener más bandas, tienen más posibles ternas, si solo miras proceso a tras fonones, que conservan energía y momento. Y entonces es tan sencillo como eso. Claro, la gracia es cómo distorsionar la red. Y entonces, si quieres un poco la idea de todo ese trabajo, es que tú, si la red es polar y si además que polar es también ferroeléctrica, es fácil utilizar un campo eléctrico para manipularla. Pero si te vas a un magneto eléctrico, puedes utilizar un campo magnético para manipularla. Al final tú lo que quieres es acabar con una estructura, un látiz, una red diferente, porque vas a tener diferentes fonones y diferentes procesos fonón-fonón.
Claro, muchas gracias, Ricardo. Ahora, otra pregunta, ahora con los cálculos que recientemente se están haciendo respecto a la figura del mérito, para
Sí.
aumentarla, uno de los mecanismos que se busca es disminuir la conductividad térmica.
Cierto.
Y hay un problema en general que tiene que ver con los modos de vibración de baja frecuencia. De acuerdo a tu experiencia, ¿hay alguna manera de disminuir esos modos acústicos?
Sí, digamos, los modos de baja frecuencia, el problema es que normalmente, no es verdad para todos, pero en general son modos de vector de onda corta, entonces de longitud de onda muy grande. Y entonces esos modos no ven defectos puntuales, por ejemplo, no ven, de hecho, si tú te vas a mirar lo que enseñé del domain wall, un modo de longitud de onda muy grande, el domain wall ni lo ve, lo salta y se queda tan ancho. Entonces, para hacerle daño a esos modos de longitud de onda elevada, tienes que ir a una estrategia más en plan metamaterial. Por ejemplo, superredes. Con una superred tú puedes ajustar el periodo de la superred e intentar inducir scattering, digamos, crear resonancias con zonas de la estructura de banda que más te interesan. Y ahí puedes ir un poco más bajo en frecuencia y a longitudes de onda más grande. Si eso lo combinas con defectos puntuales, por ejemplo, entonces ya cubres un poco más el espectro, ¿no? Porque el defecto puntual es muy eficiente en darte scattering de longitudes de ondas cortas y típicamente entonces frecuencias altas, y la superred cubre un poco de la alta parte del espectro e intenta ir a longitudes de onda más grandes y frecuencias más bajas.
Correcto, muchas gracias, Ricardo. Porque por ahí teníamos los resultados, pero es un trabajo que se hizo con cúmulos, donde se observaba un gap acústico, pero pues, son cúmulos, realmente no son útiles para materiales termoeléctricos. Pero muy interesante tu charla. Yo creo que en algún momento vamos a establecer contacto para ver si podemos.
Sí, de eso último que te comento, ahora no te la puedo citar de memoria, pero si me mandas un correo te mando un par de referencias, no mías, donde exactamente estudian eso y está muy claro, muy instructivo.
Muchas gracias, Ricardo.
A ti.
Bueno, ¿alguna otra pregunta? Pues Ricardo, muchas gracias. ¿Algo más? ¿Alguien más?
¿Otra pregunta?
Sí. Adelante.
¿Cuánto tiempo es un tiempo relativamente corto el cambio de la polaridad y de la temperatura y en un tiempo determinado vuelve a su estado normal?
Bueno, no, en principio no vuelve, ¿no? Porque digamos, si tú utilizas el campo eléctrico para hacer una conmutación de polarización, ¿de acuerdo? Eso es bastante rápido. Ahora no tengo el número en la cabeza, pero le llaman ultra fast, entonces es realmente una transición rápida. En el otro caso, el campo eléctrico siempre lo dejas encendido, ¿no? Porque si tú la polarización la tienes que estar o así, o así, o así. Entonces, tú quieres que esté a 5 grados, sola no está. Entonces, tú le metes el campo eléctrico y no lo puedes quitar. ¿De acuerdo?
Okay.
Eso, si quieres, es un poco el punto débil de esa segunda parte de la charla de modulación analógica de la conducta térmica, ¿no? Porque si tú quieres hacer un barrido continuo de todos los valores, el campo eléctrico ahí tienes que estar encendido, porque si no la polarización vuelve al ground state. Entonces, tiene que seguir apuntando. Pero
Okay.
si quieres conmutar, la respuesta es muy rápida.
Yo estoy en un campo un poco diferente, pero aplica muchísimo esto. Te agradezco mucho. Yo estoy en ciencias del espacio de la Tierra, soy arquitecto y estoy haciendo unos estudios relativos a este campo. Me gustaría después poder enviar un correo y continuar en contacto.
Por supuesto, ahí tienes mi dirección ahora en la pantalla.
Le agradezco mucho, muchas gracias.
Espero tu correo, Luis. Gracias.
Sí, gracias.